Hello, everyone. So today we are gonna get together for a new journey. We'll talk a little bit about fluid properties, why they are important, and how and what are the key measurements in mechanical and aerospace engineering and related fields. It applies to nuclear engineering, it applies to civil engineering, it applies to these uh, principles. You will find them across the board. So this is Bassam Abdelnabi from ProReady Engineer, and the best quote I like to use is knowledge lightens the burden, understanding makes it easy. You see, when you feel something is complex, it's not because it's complex. It's actually because you do not understand it. And it applies to all of us. But once you understand it, that burden goes away and it becomes easy. And this is why, in my opinion, I believe that the teacher role is about 40%, 40% in the educational process depends on the person who is teaching. He can make it easy, enjoyable, or he can be a reason of a lot of pain. So let's go over some key principles that, if you understand, they will just set you up for success. Engineers who succeed are those who have a good feeling for what things mean. So let's get going. My name is Bassam Abdelnabi. I have been working in the field of thermofluid sciences for about 24 years. I have a PhD in aerospace engineering, which was focused on gas turbine combustion. And this is actually my deep expertise. I worked about 16 years in the field of gas turbine combustion. I have a master's degree in nuclear engineering that was focused on reactor cooling, a master's degree in mechanical engineering that was focused on turbomachinery, in particular turbo pumps. I'm a bachelor degree is from mechanical power engineering. A sample of my publications are on the screen, and you can get the full list on Google from Google Scholar, if you will. My company, ProReady Engineer, is focused on offering consulting services for gas turbine combustion, as well as data analytics and thermal fluid sciences in general. We offer training for engineers in these fields, and I think the material we have and the training we have is also very beneficial to engineering students. We are focused on bridging the gap between what you learn in university and what actually you see in industry. A sample of my uh, patents are on the screen. These are essentially the patents that I have developed over my professional career so far. About one or two are missing. They are not on the screen, they are still in the works. Now, we mentioned that it's very important to have a feel for numbers, what numbers mean, and what do they exactly indicate. The best engineers I have seen and I've worked with are those, again, who have that feel. See, I can tell you the pressure is 10. And it's extremely different if I'm saying 10 Pascal or 10 megapascal. 10 megapascal is, enough pressure you can use to crush a vehicle. Typically, crushers are somewhere between 10 to 20 megapascals, and I think some upper end units go all the way to 35 megapascal. That's a tremendous number. Good engineers have a feel for the number. The better you are at that, the better engineer you will be. If you are doing an exercise of designing a heat exchanger, and the numbers comes out, I'm gonna give a simple example here. Let's say the number comes out as that the temperature estimate is 5,000 Kelvin, and that's your design estimate. If you leave it like that, you've this is very problematic. If you are an engineer working in a company and you didn't catch that, you don't have a feel for the numbers you are showing, very big chance you may not continue to work with this company if it's a mistake of that severity. It's a very severe mistake when you don't have a feel to these numbers. If you are a student at school and your professor is grading your design analysis and you just said it's 5,000 Kelvin, you put in a square and all good, very big chance you will not be doing well. A tremendous difference will be if you, after you calculate the number and it tells you it's 5,000, you put a note. You say, it cannot be 5,000. Something is off. I don't know where is my mistake, but I'm pointing it out. That one line will essentially make your professor, the person who's grading, says, okay, there's a mistake somewhere. He understands that. You take couple points off, but that's it. You see that huge difference. These are one of the small things that have a huge difference. So to be a successful engineer, you have to have that intuition, that feel. You have to be connected to the numbers, where the numbers mean something for you. Again, for this reason, as we go over my presentation today, you will see that I'm very focused on communicating that feel for you. Once we have a feel, it becomes difficult to forget. It becomes easy to remember, to assess, to build that intuition, right? Temperature. When you work with thermal fluid sciences, when you work in different fields, almost all fields maybe, it's a good guess to make, temperature is very important for us. I want to talk to you today about temperature, about pressure, about density, about viscosity, and on and on and on. All these. When I want to talk to you about them to set you up for success, I want you to understand not only what they mean, which is what you would find in your textbook, is what they mean. I go beyond that. I want you to know what they mean, how much is a lot, how much is too low, how much is an intermediate. I want you to know how do we measure it. And if you know those three things, what does it mean? What's the order of magnitude? How do we measure it? You are on your way to succeed, right? Temperature is a measure of the kinetic energy of the particles in a system. It's a very dry definition. I don't like it. Okay? But a much better is that second line item here. It's the degree of coldness and hotness. That resonates right away when you say degree of how something is very hot or cold, because that's how we feel, right? So this second line item is really what makes sense, is what I want you to remember. Now let's build a feel for it. You see, temperature, I started with it because everyone listening to this will immediately relate if I tell you it's freezing. You know what does freezing mean? You know what it implies. You know how it feels. You know what happens. If I tell you this is boiling water, you know it's too hot. You know it will burn your skin. You know you have something to compare to. You know that water boils at 100 degrees centigrade. 212 F Fahrenheit. So if I tell you that temperature is 3000 F, you say, boy, man, this is a scale, this is tremendous. In fact, even if I just tell you the temperature is 1000 F, you say this is humongous. 1000 F is humongous because 212 will boil the water. You're talking here a lot of temperature. See, that's the feel we are talking about, right? So to give you a little bit more feel, grilling, when you go outside grilling, that temperature is somewhere around the 400 to 500 degrees. You can relate to that because your hand, when it goes about on the top of the grill and you spend a couple seconds close, it really is, hurts, and you can't even keep your hands, and you have to move it quickly, and you can get it closed down. You have to keep it up so the temperature is lower. You can relate when I tell you that the temperature is somewhere around, the 400 Fahrenheit, give or take. You see, steel, that metal steel, it melts. It just gets oxidized at about 2800 F. It disappears, right? So now that temperature 2800 F means something big for you. So for example, just to give you one example, you say, well, if steel melts at 2800 F, different kind of steels melt at 2800 F. If I make a device that a flame lives in, right, combustion systems, which is my deep expertise, if a flame lives in and that flame is 3200 F, you say, hold on, 2800 the metal melts and this 3200 is sitting in something. You have to be doing something to cool that down. You have to. You cannot say, here's the combustor. The combustor is like the place where the flame lives. Some other presentations, if you look at my combustion arrow presentation, you know what's a combustor. That is that entity that surrounds the flame. So if I tell you there's a 3200 F flame in there, you will say that metal temperature is probably something like 1600, 1700, 1800 F, and that's about it. It's never going to be 2800. It's never going to be 2600 because this temperature, the structure will already melt. It doesn't exist. So somewhere, somehow, someone did a trick, and you will learn those tricks. I actually introduced that in my combustion aero engineer presentation. If you haven't seen it, please go ahead and take a look at it. But there are tricks that make that structure cold enough to sustain that flame sitting inside. And here is again the sun temperature. It's about 5000 degree Kelvin or 5000 degrees centigrade, doesn't matter much. It's a joke. A friend of mine, I was telling him what's the sun temperature. He said, I don't know. I told him that's 5000. So he said centigrade or Kelvin, and we had a laugh at it. Now the reason we had a laugh is, the difference between centigrade and Kelvin is you add 273. So what does it even matter? What's the difference between 5000 to 5200? Right? Now engineers are smart. They use order of magnitude, representative numbers. You will not be a good engineer if you are the type of engineer that says the temperature is 325.265781. No. You cannot do order of magnitude. You do not understand when are decimal points needed and when they are not needed. Don't do that, please, as an engineer. Now, so temperature is important. I just convinced you it is important. So how do we measure it? Well, thermocouples is the number one. Thermocouples, RTDs. What is a thermocouple? Like literally, it's a wire. If you've seen a thermocouple, it's like a wire. Now, and there's a version of it that's not a wire, that is as big as that thing on the screen, like a pen, like so thick, beefed up and thick. So when do we use the big one? When do we use the small one? Well, it depends on the application, but it doesn't change the fact that this is a thermocouple. And the RTD is similar to it. It sort of looks like that, but it sits sometimes in a well. It has a different shape, but it's similar. And there is the optical pyrometer, something like this. You've probably seen it, like, they sell them in terms of camera. Sometimes they do it even in your cell phone, I believe, right now. And you hold this handheld devices, you point at the thing you want to look at, and it plots, to you like an image, a thermal image with the temperatures on it. These parameters sometimes are very nice, useful, and good to do checks on equipment when you are walking in the middle of equipment and you want to make sure of the surfaces around you. You hold that thing in hand and you keep pointing at structures around you, and it essentially gives you a read of the temperature. Some of them are guns that you hold in hand. And essentially these guns that you hold in hand, you aim it at the surface, and essentially you click a button, there's a laser comes out and it goes to the surface and it gives you a read on it. So now you know the magnitude of temperatures, how it's measured, what does it mean, and if we continue this way, when we talk about pressure, density, and on and on and on, then by the end of this presentation, you will be feeling very well that you understand why those things are important and how do we measure and handle them. Let's talk about pressure. Pressure is less common than temperature. And immediately I will mention here your tire, your car tire. When you go to your car tire, you see that inflated thing, right? And you've probably maybe seen some of these like ruptured before. That rupture comes with like some sort of you hear a big bang. A bang happens when it ruptures. When you fill it up, you connect a compressor to it and you set it to 32 psi, 34 psi, 36 psi, 30 psi. This is pressure. This is pressure. What you are doing is you are adjusting the pressure of the tire. That's what keeps it inflated. Now, that pressure is very simple, actually. It's many times, students, engineering students, they get, they don't feel well about the definition of pressure. It's the force. The force the fluid is pushing at that point. The force at that, per unit area is the definition of pressure, force per unit area. That's it. If I have a container, I bring you a container, a bottle. You have a propane tank to your home that you use for grilling, right? You've seen that. That container, sometimes it comes with a pressure measurement gauge like the one on the screen here, right? And it's sitting up top on it. And when you look, it will show you a number. That's the pressure. It's telling you that what's inside is pushing against all these walls with this pressure you are reading, right? So that's the pressure. So, to build a feel for the magnitude, your passenger car tire is about 30 psi, 35 psi, give or take. A truck tire is 100 psi. Now I want you to feel what is 100 psi, so I brought you this from YouTube. It's actually as a video, but I did a pause here. That's pause that and take a look. You'll be amazed, right? They use these cages with the car tires, and this was just a maquette, and then it exploded. Take a very close look here. Do you see this thing that looks hazy? Looks like a cloud? What is that? You see, as the explosion happens, and because the pressure was extremely high, when it ruptures, the air speed coming out is extremely fast. And there is very strong density change. And what you are seeing here, this cloud kind of thing, is a density change. It's because density changed, right? And this is actually supersonic, right? This is extremely high speeds. And it's so high. It's so high that this pulse, this thing running out with very high momentum, it hits the maquette and just, the maquette, even his head is still, you see, the head is still here and the thing went away, right? Very dangerous. Now that's 100 psi, 100. You see, imagine we are taking a walk in a plant somewhere and I tell you, well, we're going to go into the compressor room, right? Where the pressure is somewhere between 500 to 1,000 psi. The flavor will be different. The flavor will be different. You say, oh man, this is high pressure. I want to make sure when I go in, things are safe. I'm not listening to anything or something like that. That is a sign of something is about to break or to go somewhere, right? That hissing noise is sometimes normal part of plants that you hear that hissing noise, but you always going to be careful when you hear that. There's going to be pressures that are high. Now, high for you means something, right? Because what does 100 do? So an aircraft engine runs at somewhere around the range I've given you, between 500 to 1,000, like 700 psi, give or take. Your water, when you open your water at home here in the US, that's about 70 psi, give or take. So now you have a feel for the magnitude of pressure and for what it means, right? How do we measure the pressure? So if I tell you let's measure pressure, what do we do? Well, the Bourdon tube right here, the pressure gauge, it's called the pressure gauge, is like, extremely, extremely famous. You see it on tanks, like I said, on the propane tank, and you see it on gas cylinders, right? It's very famous and we like it. You know why do we like it? It's just because take a look at it. I mean, you have it's gonna just point and tell you that's 40, that's a 60, that's 100. How do you make it easier than that, right? Now, or you can see these are electronic, and sometimes they come with a little screen that you can attach an option. You can request that when you buy them, and sometimes not. When showing the number, nobody's looking at it, like it sits in a place where nobody is allowed to even walk in. So okay, but to be honest with you, in all my test cells that I built, I always still would purchase the option with this little screen on it, because I always want to see a number, and irrespective of somebody is walking or not, because even when we run the surveillance cameras, I like to see the number showing on that transducer, if you will. Now, or this one, this is an industrial transducer. These are typically extremely accurate and very expensive. Orders of magnitude expensive more than this and that. And these are orders of magnitude expensive more than this, right? So the price kind of goes up this way. This can be extremely accurate. This industrial pressure transducer, extremely accurate, and the price depends on what brand you are buying. There are many, many brands. Top brands are Yokogawa and Foxboro now are doing really well with their new transducers and high accuracy unit, and they're very cost effective. Yokogawa is like the best. It sells in around $2,500 to $3,000, if you will. The Foxboro goes somewhere, starts at the $1,600 as you go up. Again, they are very competitive now with the new units they have. Now, beyond what I'm trying to say here, but okay, now you know. Now you know. If you want to measure pressure, what do? You have a feel for the pressure. The pressure is simply the force the thing is pushing by. Good. Move forward. Heating value. Now, you see, we went from temperature, that was very common, to pressure, less common, to heating value, that's even less common. You see, heating value is a very nice concept. It simply means the heat content. Think of it, the amount of energy in the thing that burns. To the most part, we use that for fuel. We talk about fuel heating value. See, fuels like hydrogen, like natural gas, like the gasoline in your car, like the diesel, like the jet A that sits in an engine, like the coal, like the whatsoever. These are all fuels. You see, we burn them. Why do we burn them? We burn them because we need the energy stored in them. If this cup is a cup of diesel, as it sits, there's no value. If I have diesel sitting here, that's doing nothing. Now, the value of this diesel is when it burns and releases the heat, whether it be because you are using it for heating purposes or for power, like generating work from a car engine burning diesel. What is a diesel engine? What is a gasoline engine? Your car, what does it do? Here's the car. You put fuel somewhere and you release the energy and you change it to the tires. You go from this to the tires spinning, right? Energy is converting itself from this to heat to work. So heat, the energy when you burn this, what will get released is the LHV, is the heating value, right? By definition, take 1 kilogram of the matter, burn it, and we say it's X kilojoule per kilogram or megajoule per kilogram, right? Or if you are using British units, or US units, you say BTU per pound, right? British thermal units per pound. Energy per unit mass. If I take this 1 unit mass and burn it, that's what I get. Very simple. Now, let's build a feel for it. Let's build a feel for that energy. How much is that typically? You see, if you use this number, if you say liquid fuels, meaning things like diesel, like Jet A, like kerosene, like gasoline, see all these families, if you say give or take it's about 20,000 BTU per pound, you're not very off, you're doing reasonably well. 20,000 BTU per pound, or in SI units, 45 megajoule per kilogram. 45 megajoule per kilogram. Good enough. You see, when we express that heating value, the amount of energy in something, we either use it per kilogram of the thing or per unit volume of the thing, right? Now, why do you think we like per unit volume? This chart here. What is this chart doing? What am I trying to communicate to you? It's again the LHV, which is energy, but per volume. I think this should have came across to you. The reason we like volume is it relates to how we will store the fuel. Think about that. Your car, you go, you fill it up, you say I've put in 17 gallons. That's volume. You put in it 17 gallons, like a gallon of milk, 17 of that fuel. We like to know, because we are going to build a volume. The tank, gas tank is a volume. We're going to put an amount of fuel, and you want enough energy. You want enough energy so you can drive for a couple days. So we like energy to be expressed in terms of volume because of transportation. It's going to take a volume. It's going to take a volume to put in it, right? And when you think in terms of that, you will see that, take a look here on the gasoline, the diesel, the ethanol, and the biodiesel. Take a look at this family. What do you observe? Say very large. If you use 120,000 BTU per gallon, that's a reasonable number to remember. Now, take a look. Compare it down to here, to liquid hydrogen and natural gas. These numbers are tremendous. You know what does that mean? You can get tremendous amount of energy from a small amount of fuel. Now you know why aircraft engines fly with this liquid fuel, because it will carry a certain amount, but that certain amount has tremendous amount of energy. It doesn't, they have been speaking about using hydrogen for powering these aircrafts. And there are a couple challenges with that. One of them is, look at the heat content of that hydrogen versus the other liquid fuels that we typically use. That's one problem. The other problem is, where is the hydrogen? Where do we bring the hydrogen from? Just think about that. These fuels, these liquid fuels are under the ground. You just, drill, comes out, here you go. Now it's oil, you get refined, but it's there, it's sitting in the ground. So where is the hydrogen sitting? It sits nowhere, there's no hydrogen. We have to make it, as that's a different story. Okay, but anyways, so LHV knowledge is extremely important. It's how we say this fuel have this energy in it, and I can take that energy and make work. Drive my car means make work, because it's spinning. You've generated work, that's work when the wheels are spinning, right? I change that heat to work. Or I take that stored heat, I burn it just for, like when you sit in your home and you turn the heater on. If it's a natural gas heater, then you're burning natural gas to make the air warmer, right? You're taking this energy to heat the air. So we want that LHV for many things related to engines and boilers and furnaces, analysis, if you will. This is where you will see it. How is it measured? Well, two things come to mind. The gas chromatograph sort of looks like that, not necessarily what you will see in the field, but this is one example. And the other device is the wobbemeter. These devices, they run in the field with gas turbines, and essentially the gas goes in, you measure, tells you, well, this gas I am burning right now has an LHV of 19,000, 18,000, 20,000, 21,000, right? BTU per pound. And the wobbemeter does the same. And I'm not trying here to go into the details, why two, which is better, why do we do this? All this information is extremely important for people who work in combustion in gas turbines, but I'm not going to go over that here. I'm just scratching the surface for you to set you up for success so you know what the value means, have a feel for it, and what measures it. Good. Density. You see, density is very simple. It expresses mass. You see, density by definition is mass per unit volume, the amount of mass that you put in a volume. Not only mass, it's the mass in a unit volume, right? Let me try to make this easier for you to comprehend that story of mass per unit volume. Here's density rho. It's m over v, right? Mass per unit volume. Now, let's use SI units. You will know why in a second. Put mass in kilogram and volume in meter cubed. And that would be the density in kilogram per meter cubed, a very famous unit to express density. Now, take the kilogram out and put it 1,000 multiplied by gram. 1 gram, 1 kilogram is 1,000 gram. So that's what we have here. Take the meter cubed and instead put 1,000 liter. Why is that? Because 1,000 liter is 1 meter cubed. Now, 1,000 goes to 1,000, goes away, and it turns out that the density is the amount of grams you measure in a liter. Let me repeat that. Let's look at this experiment here. What we will do is we're going to bring a jug, a 1 liter jug. 1 liter, it has to be, because that's what I just told you here. Fill it up. Measure the weight in grams. And the number it will read will be the density in kilograms per meter cubed. And these are all very representative numbers. For example, the very famous water here, water, 1,000 kilogram per meter cubed. Water density, 1,000 kilogram per meter cubed. Let me tell you how to build a feel for this. You see, if you have a 1 liter Pepsi bottle, you go to pick it. Let's say this is a 1 liter Pepsi bottle. So you go, you hold it. You don't have a problem. You did that because you know that the density is 1,000. So actually, this is 1 kilogram. That bottle, the bottle you picked, weighs 1 kilogram. It's nothing. It's going to be very, very light. You see, if you fill that same bottle, take the same bottle, put mercury in it. That's mercury here. And this actually, I lived through this personally. And it was a very day that I never forget. And this is why actually I'm showing you this example. So I was in the lab with my advisor. That story is about, 20 years ago. So I was with my advisor. In fact, it's more than 20. I was with my advisor about 25 years ago. And there was a bottle, 1 liter bottle actually. And it had mercury in it. So he said, grab this bottle of mercury, please. So I went to grab it. I went down, and I'm holding it and I'm trying to pull it, and I felt that my shoulder and hand are being ripped off. It was, take a look at the number here. The density is 13,500 kilogram per meter cubed. You know what does that mean? That this 1 liter bottle was about 14 kilograms. Now think about that. Your perception, my perception, was that the bottle is 1 kilogram. So my body knows the amount of force it needs to pick 1 kilogram. I went there, I didn't think that I'm picking in the same bottle that I know it's 1 kilogram. It's not 1 kilogram, it's 15 kilograms now. The bottle, my perception is different, it's 15 times heavier, right? So density tells you, it brings into perception that the mass in a volume, so when you go to carry, to transport, to, and density comes for many reasons and many applications. Forces, buoyancy forces, forces on an aircraft engine, drag, lift, friction in pipe, pumping power required to pump fluids around, density will show up in all these engineering calculations. If you keep scanning here, you would build another field. Steel is about midway, right? Oil is less than water. You see, all those things are very important. Air is nothing. Air is like 1. You know that 1 liter bottle? It's empty, right? It's nothing. It's 1 kilogram per meter cubed. So essentially, the weight of the air is 1 gram. Nothing, essentially, right? Natural gas is even little lower than air. You see, in water, if you throw a piece of steel, we all tried that experiment. It sinks right away. You throw it in, it sinks right away, right? Why is that? Because the density of steel is much heavier than the density of water. If you have piece of wood, you throw it in the water, it floats. Right away it floats. Why is that? Because the density of wood is less than the density of water. So I've just given you an example now of where density is important to know and understand in flotation, right? You will learn that in fluid mechanics. Okay, good. All right. Let's go to the concept of specific heat. Let's pull the pointer out. Okay. It's knowledge, understanding, have a taste to it, a really nice taste, and that's for all human beings. You don't need to be smart or anything. Every single human being, when you understand and you build the feel, you actually feel pleasure. So specific heat relates to our day-to-day life. The concept of specific heat is actually very simple. It's the amount of heat or energy you need to provide to heat something 1 degree, and that something will be 1 kilogram, right? This is how they made this property. Now, I know this may not have come across as easy, but actually it will be in a second. You see, if you take 1 kilogram of water, so take a 1 liter bottle, fill it with water. That's 1 kilogram right there. How did I know that 1 liter is 1 kilogram? You know that from my presentation earlier when I spoke about the density. Take this 1 kilogram, put in a pot on your stove, turn the heat on. Measure the temperature. Keep heating up. After the temperature increases 1 degree Kelvin or 1 degree centigrade, the amount of energy that went into the water will be about 4 kilojoules. So 4 kilojoules are needed to increase the water temperature 1 degree. Measure the temperature and wait until it's 10 degrees. At around 10 degrees, you have added amount of energy that is roughly 40 kilojoules. Because it's 10 degrees. You put in 40 kilojoules. You see, you'll tell me, but you are saying there water specific heat is 4.18 and you are using 4. Well, that's what I taught you today. You want to be extremely successful and just crushing it is when you simplify the numbers and reach an estimate that is reasonably accurate in a couple minutes. I have worked with people in my professional career who are in advanced roles, and we will be having a chat, and someone in particular comes to mind. I'm not going to say any names. I'm not trying to embarrass anyone, but someone who's like very influential and working at very in very advanced, he has an advanced position, and I did an estimate in 1 minute. And he was struggling, we need to put the numbers together. We need to put the number in an Excel sheet. Let's just do the math. I told him, well, I just did the math for you. This is what it is. And when he went and put the numbers in an Excel sheet, he came back with a number that was somewhere between 5 to 10% different than what I estimated in 1 minute. Just while we are chatting. This is the power of doing order of magnitude analysis. This is the power of knowing what the numbers mean and be able to use them to do quick estimates and quick validations and quick designs. So let's say 4 kilojoule per kilogram for the water. Now, where does CP, this specific heat concept, comes into play? When you go to the sea, it comes into play. You see, early in the morning, let's say it's 9 a.m., you're taking a walk. You touch the water and say, boy, the water is cold. 10 a.m., water is cold. 11 a.m., water is cold. See, what's going on? The sun is up. And the sand you are walking on is hot, is picking up the temperature. Air feels warm. You touch the water, it's cold. The opposite happens at night. Sunset happened. It's dark. You are taking a walk. Air is a little bit chilly. You touch the water with your foot and what's going on? This water is warm. It's 8 p.m. It's 9 p.m. The sand is cold. Air is cold. Water is warm. This is all specific heat. You see, air specific heat is 1. You just need 1 kilojoule and temperature goes up right away 1 degree. Water takes 4 times that. So it takes tremendous amount of time, all day long with the sun up. The sea is absorbing heat, and it's going up in temperature. And it takes a while for the heat, all that heat consumed to dissipate. But the air is changing very quickly. Let's say you're going to build a heat exchanger. Now, I know some of you may not be comfortable with the term heat exchanger, but these are an extremely important device. They sit in your own home. That water boiler in your basement? That's a heat exchanger device. The AC as a heat exchanger device. They are everywhere. Heat exchangers are. You know, in your car, radiator, that's a heat exchanger device. And on and on and on. Now, let me tell you, heat exchangers are very simple. You know, as the name implies, just think about the name. Heat exchange. Something is exchanging heat with something. You are either trying to heat something up or cool something down. Depends on what you are trying to achieve. Here is the fun part. If you are using water to cool something, or using air to cool something, the size of that device, or water is running to cool something, will be maybe 1/4, 25% of the size where you are using air instead of water to cool something down. And let that sink in. Why is that? It's very simple, because of the specific heat. Water can absorb tremendous amount of heat for a very small increase in temperature. Cools down very good compared to air. Specific heat is a beautiful concept and very important for us to know, understand, and digest. You see, there's a CP and CV, and the difference between them is that process I just explained. Actually, if it's a liquid or solid, like water, or solid, like a piece of metal, it's very reasonable to say, well, it doesn't matter if pressure is constant or volume is constant. These are incompressible. It's the same number. The CP is a CV is a C. Now for gases, the situation is different. The story is different for gases. Gases, if you do this experiment I just said, they will be different if you are holding pressure constant or holding volume constant. They will be different because it's compressible and it's going to expand, it's going to change in volume. And in fact, the ratio of CP and CV for gases is important. It's called gamma, and it's an important number in thermal sciences. So there's another piece of information I want you to know, that this CP or CV is not necessarily a fixed number. It may actually change with temperature and pressure. Depends on your application. But using an average number works perfectly fine for engineering design purposes. So how is it measured? Well, you can think of what I just said, and this is where it comes into place. They call these devices calorimeters. A couple examples are on the screen, and essentially bump calorimeters, they are more of used for LHV, heating value measurements, but the concept is the same because you're trying to hold the volume constant. So relates to the CV, and the DS calorimeters, they are more of used for CP measurements. Now, having discussed the concept of CP and the amount of energy to increase temperature, now immediately comes into discussion something called enthalpy, H. See, by definition, enthalpy is internal energy U plus PV, pressure multiplied by volume, and this is specific volume, so essentially 1 over rho, so P over rho, or PV. Enthalpy expresses the amount of energy at a certain temperature. Expresses like reflects, gives you a meaning, a feel for an amount of energy. By itself is not a very useful number. What is actually useful and comes into play in engineering design calculations and problems is delta H, how it did change. that delta H is of significance for us. Let's go back to the example I did a second ago with you on the previous slide when we spoke about water. If you look at 1 degree difference, you get the CP. You turn it on, 1 degree. That's a definition of CP. How about if I do the 10 degrees thing? That's now a delta H, which is equal to CP delta T. Let me say again. Enthalpy H can be calculated for water as Cp multiplied by temperature, Cp times T, like here. You say, but I see a Cv here. Well, we discussed on the previous slide, it's a Cv, it's a Cp, it's a C, it doesn't matter for liquids and solids. That C times T gives you the total enthalpy. And if you get the difference of enthalpy, so water temperature changed from 25 degrees to 100 degrees. Multiply Cp by that delta T gives you the total energy you moved to heat the water up. If I want to calculate from your stove the total amount of energy delivered to the water, in the previous example from the previous slide, it's very simple. Say temperature change from 25 to 100, get the difference, that's 75, multiplied by Cp, and here you go. Here's the total amount in kilojoules, for example, that I, moved to the water to heat it up. You see, that concept of delta H is extremely important for us because in future presentations, when we speak about engineering devices, turbines, compressors, pumps, when time comes, you will see that the power consumed or the work you need on a compressor directly relates to the enthalpy change from input to exit. You take the air that you compressed. You see the delta H. That's the power of the compressor. That's it. Simple as that. I'm not going to expand more on that for now, but I want you to know that it's very important for that purpose. Now, having said that, because I just told you that, you see, how do we, if I'm an engineering person and I'm trying to get the H, where do I get the H from? Well, I gave you one example. Use Cv or Cp or C times T for liquids and solid. That will work well for your application. You'll get the H. If it's an ideal gas, there will be a Cp and there will be a Cv. And Cp by T you get the H, Cv by T you get the U. Difference between H and U is RT. R is the gas constant, just in case if you don't know what gas constant is. It's a constant that is determined based on the gas type. So how that is, it's a universal gas constant, R bar, divided by the molecular weight of the gas. In a separate presentation, I will talk about these fundamental calculations, which is essentially comes from thermodynamics. But for now, I just want you to know that it's RT, and the difference between Cp and Cv is actually the gas constant again. That difference, the reason there is a difference between Cp and Cv kind of thing, is actually it relates to that gas constant. So we know how to do if it's an ideal gas. We know what to do if it's a liquid. How about if it's a real gas? Now, real gases, it's sometimes a reasonable assumption to assume that air is an ideal gas and use simplified equations and calculations, and you will be doing great, fantastic, like I told you before. You'll be very nice, very good, very, very reasonable estimate. But sometimes it's not. it has to be dealt with as a real gas. Now, real gases, we use something called equation of state, again, beyond what we want to say now, but let's say complications come into the estimate and the measurements. Steam, for example, is not an ideal gas. It has to be dealt with this level of complexity. Likewise is R134A, that's a refrigerant. Just in case you've never heard what's a refrigerant before, you know, the fridge and the freezer, your AC, things that make things cold, work using a medium like R134A, which was in the past more commonly a Freon. In a different work, we'll discuss about these concepts and why these working mediums, but for now, know that this is the medium in your car. AC has R134A. When you are designing that car for your, AC for your car, you need H, the value of H, because I just told you there is going to be compressor. The most part of your car, there's a compressor sitting there for your AC. If you want to calculate the work, it draws power of your engine. It's driven by your engine. That work is essentially delta H. So where do I get the H from to do my design and calculation? And you get it from this chart up top here. It's called the pH diagram. That's really your source of information. It has pressure on the y-axis, H on the x-axis. And I'm not trying today to go over this level of details. Again, it's a separate topic, but very quick. You see this line, this line, this line. These are constant temperature lines. And but before I say that, you see this envelope kind of curve. Actually, no, I should have said that it's actually this and this. You will learn that these are called like saturation lines, and what that is there's a phase change. Phase change, it's like when the water turns to vapor and when the water turns to ice. These are changes in the phase of the material. So let's say that you have a certain operational conditions you are running at, and you want to know what is the value of H. These 10%, 20%, 30%, 40%, all these numbers, all the way until you are 100% here on this line, is actually the percent of vapor in the mixture. Let me say that again, beyond what I'm trying to cover here, but I just want to give you a taste of something. This is liquid. And as you progress to the right, it's changing from liquid to vapor. And when you reach here, it's now vapor. So the percent is the percent of vapor. You go from 0, there is no vapor here, all the way to 100%, right? These are called state diagrams. Extremely important in thermal fluid sciences and design calculations. Extremely important. So let's say that the problem you are solving is you have a certain temperature that you know and a fraction of vapor that you know. Let's say it's 0 centigrade, and let's say it's 40% saturation. Then it will be this point right here. This is the 40% line. This is the 0 centigrade. You get a point. You come down here. You get H. So now you have the enthalpy. This is how these diagrams work. You use some information that you know to get a point, then you go down and read what you want to read. Some of you will probably have a question, what is the red? What is this red here? And I'm seeing like something that says compressor. Something is happening here. Well, this is a refrigeration cycle. It's your AC in your car. It works this way. Beyond what we want to cover today, but just giving you a taste that actually the reason we use that, this is your evaporator. It's the unit that sits behind your dash kind of thing, and it sucks the heat and gives you the cold air in. And this process of sucking the heat and giving you cold air, the delta H, you can literally read off the chart here. Like just take this delta right there. And this delta, like this is the energy you sucked from the air, that hot air in your vehicle, you sucked that energy from, you cooled it down. The delta H, you're going to say this is equals to m dot Cp delta T of the air. And now the air temperature has dropped because I pulled that energy out of it. And here you go, I have cold air blowing out. Now, down here is a second example of a real gas where we want the value of H to do analysis. Steam turbines. You've probably heard somewhere about steam turbines. You have to. You see the power when you switch lights on in your home is mostly coming from steam turbines running to generate power. Yes, there are gas turbines, there are water dams, on and on and on, but steam is a very big part of power generation. These are efficient cycles. They are very solid. They run baseline load, meaning year long they are running. All these terms maybe we'll have an opportunity to talk about in the future, but my point is, the reason you switch the light on and it comes to your home is a big probability it's actually coming from a steam turbine. Now, this steam turbine runs steam. We want to calculate that work, that power that goes to drive a generator, and now my power is on here. Then you need the delta H. You will have that turbine. Steam is coming in hot, steam is going out cold. You extracted this heat to spin it. And that's why it's spinning. You spin it, you put it on the generator, and now you have power in your home that's coming to you from a facility. So as an engineer, you want that delta H. Where do I get that from, Steve? Called Mollier chart down here. This is called Mollier chart. There's a reason that this is the H you are interested in, and this is entropy. S is the entropy, which we'll talk about. And a second ago, I spoke to you about saturation lines right here. This red line is an example of a saturation line. And these lines are constant temperature line. You see they have some sort of a curvature. This is a temperature line, a constant temperature line. And these are pressure lines. These are pressure lines. And as we discussed, if I give you a pressure and a temperature, like let's say this is your pressure and your temperature is 400 degrees. Then you intersect them, you get a point, you go to the left and you say my H is 3,400 kilojoule per kilogram. Or you go down here and you read the S if you need S. When you take steam cycles, or if you know about steam cycles, or maybe at some point in time I will give some analysis on the steam cycles, then you will see how we can use this chart. In fact, fun fact, if you go to get your professional engineering license, all those things that I discussed here will pop up in your exam. as a professional engineer. You know why is that? Because these are the basics of engineering. If you don't know that, there's a big problem. You don't know how to use those things, what they exactly mean, how to use these tools. And I think this is a very important input that I said now. You see the information I'm going over. This is not trivial. This is not like useless. This is extremely important. It goes in a professional engineer certification exam, right? Okay, good. Alrighty. Entropy. Entropy is a very interesting property. Engineering students struggle to understand it, and they have the right to. I do believe that very few people can actually educate engineers about entropy and what its value. So if you don't like it and you feel intimidated with entropy, you have, I can understand, I can relate. But it's actually not as bad as you think. Let me show you. Entropy is a property that is used to indicate randomness or disorder. A good way to think about it is if there is a lot of things are getting worse, entropy will increase. And when things are sorted out better, entropy decrease. The universe we live in as a universe, entropy is always increasing. Every single day is increasing. And this is why eventually there has to be a judgment day and death, and a day we're going to be taken back to the one who created us. Because it cannot just be always getting worse and worse and worse. I mean, there will be some point where it has to come to an end. That entropy that measures disorder is extremely useful in quantifying how efficient machines operate. Let me tell you more. A very famous device is called compressor. You may have one sitting in your home that you use to inflate your tires. This compressor, the reason you have it is you're trying to add pressure to the air. Now, it's not going to do that except by pulling power from somewhere and then adding that energy to the air. Typically, you're going to plug it into your lighter. It has a battery. Put it in an outlet. It's taking electricity, then adding energy to air, and now you have energized air that you feed in your tire. That's a compressor. This is a compressor. Now, there's a reason that these compressors, when we depict them, when we plot them, we make it big here and small there. And we say this is one, we go from the big, we exit from the small. And what we are trying to do when we do this plot is a couple things. To say that it's compressed, like if you take a bottle, you empty that bottle, you stand on the bottle. The bottle will essentially compress and will reduce in size because it's compressible. So it will reduce in size and pressure will go up in your bottle. For it to compress, it needs work. It's going to withdraw work, power, so it can compress the air. There is something called irreversibilities. Irreversibilities are things that waste energy, and there's little you can do about it. You may be able to improve it, but you will not be able to eliminate it. It's friction. If you are trying to move a box in your basement, a very heavy box, 10 feet. And let's say you are pushing it on the ground. You know, if you were moving it on a carpet, is different than if you were moving it on bare floor, and different if you were trying to move it on wood. And in all cases, you're just sliding it over it. And all these differences come from friction. You wish there was no friction, then the pushing would have been much easier. The force that you need when there's more friction, you need to put more force. You know what's the only reason you're putting more force? And it's getting wasted. It's because there is more friction and that's it. You have to pay more than what you need to overcome this waste. If you get a compressor and all the target you need from the compressor is pressurize the air to me from 14 psi, atmospheric 14.7 psi, take it up to 100 psi. That's what I want you to do. If this compressor was ideal compressor, there is no losses, there is no friction, there is no secondary flows, there is no separation. Don't worry about these terms. They are actually very easy. Again, you understand, everything will be easy. But all what I'm trying to say is, if there was nothing, it's ideal, it's perfect. Let's say it was going to take 1 horsepower to give you what you want. If it was ideal, but it's not. So when you hook it up to your power outlet, it's withdrawing 1.1 horsepower. Why is it taking more? Should have taken 1 horsepower only. It's taking that additional power to compensate for the waste. And you end up with the 1 transferred to the air. Why are we talking about that in entropy? This is why entropy is needed. Entropy will quantify, gives you a method to quantify these losses because of inefficiencies. Let me show you how. This is called a state diagram. Again, you've seen it in my presentation. Here's H, enthalpy. You know that. Or it could be temperature. Why? Is it for air, H or T? You got it right, because H is equal to Cp times T. You can plot H or T. Will be very similar. Entropy on the x-axis. Here is P1, here is P2. Here is 0.1. What do you mean 0.1? Just ambient temperature. Here's ambient temperature, right? You go on this curve, you put ambient temperature, and you intersect ambient pressure. This is ambient pressure. So ambient pressure, ambient temperature, you give you a point. This point you have here, you've now identified a point on the state diagram. And from 1, we're going to move into a compressed state. So 1, right? If you have the compressor sitting right here in front of your eyes, right, on your desk, 1 is what's coming in. We call this state 1. It's going to move to a state 2, and this is state 2 here. You see, if it goes with the entropy constant, this is S entropy on the x-axis is the same. S1 is equal to S2, and we say this is 2S, meaning 2 state 2, the exit of the compressor. Assuming entropy is the same, TS. This is an ideal compressor. This is the perfect compressor. It takes you from 1 to 2, and it doesn't change the entropy. It doesn't change the disorder. It doesn't have inefficiencies. It doesn't have friction. It doesn't have any of that. It goes from 1 to 2. S. Will you find this device? No, you won't. It doesn't exist. This device does not exist. What actually happens is you're going to go from 1 to 2 on this path. and 2, you're going to get the pressure you want. But 2 will be little warmer than 2s, and this is called 2r, like real, and you can just make it 2. Will be a little warmer. Why is it a little warmer? Because of all the things we said. Reality is entropy will increase. S2 is larger than S1. Oh, I hear you. I hear your mind. I'm reading your mind. You say, but you said it's gonna give me a measure of inefficiencies. Where is that? Now let me show you. This is called the compressor efficiency. How efficient is your compressor? It's actually a very simple concept. It's the work that is the best and least and minimal. You remember the example of the 1 horsepower? This is what you have needed ideally. This is what you needed ideally. Divided by what you actually sucked from the grid or from your outlet, or like the real work. You divide this by that, this is going to be a number less than 1. If it was 100% efficient, then your isentropic work is your work, they are the same, but they are not. What's going to happen is that your real work is more than your best isentropic best work. You see, work, I already told you, if you want to know this is your compressor and you want to know the work, it's actually very simple. See how the enthalpy changed from inlet to exit. Air was coming in with a certain enthalpy, 300. It's coming out with 500. What happened? Why did the air enthalpy change from 300 to 500? Because it sucked 200. That's it. Very simple. It's energy balance. In a separate presentation, I'm going to go over the details of energy balance on all machines. That will really enlighten you and makes it a very simple. Lots of complaints I hear from people on actually performing these simple energy balances. So we'll elaborate more on it. But for now, actually, it's as simple as I said. You see, air is coming in with $300. It exits with 500. What happened? Well, it took 200 from somewhere. That's as simple as that. And that work, right, is if you divide that work, this is if it was very efficient. See this delta? If you measure this delta, as if it was very efficient. But it's not that efficient. So it'd be this bigger delta. It's this bigger delta. And now you calculate your efficiency of your compressor, and now you say my compressor is 85% efficient. How were you able to know how efficient is your compressor? Through the entropy concept. Like here. Entropy concept allowed you by saying if the entropy was the same, this is the work. But truth of the matter, it's not. Now I have an efficiency. Now if you make your compressor go from 85% efficient to 87% efficient, great, to 89% efficient, awesome, 91, oh, you're doing better. I think right now the best we've reached in making of compressor is 95%. You can immediately know why would it be better, because you are improving from a friction standpoint, secondary flow standpoint, separation standpoint. We'll talk about that in a more advanced presentation, but here you go. Entropy allowed you to make a judgment on how efficient is the process. See, the entropy is beautiful. It's very nice. It really helps. It's great. Let's talk more about entropy. Entropy for a system doesn't necessarily have to increase or decrease. There could be a process that happens and entropy decreases in that process. Like you are removing heat, entropy will decrease. However, entropy of the system that is all inclusive of your surroundings will always increase. This concept may be a little bit difficult to digest, but not as bad as you think. Bear with me. You see, there's a second law of thermodynamics. You see, the first law of thermodynamics is very easy. I already told it to you. It's energy balance. $300 coming, here's 500 exiting. What happened? 200 came somewhere. It's 500 coming, I'm exiting with 100. Well, you spent 400 somewhere. That's energy balance. That's straightforward, not a problem. That's first law of thermodynamics, energy balance. But what is the second law of thermodynamics? That's where the entropy comes into play. It says that entropy forces processes to happen in a certain way. It has to obey that. If you calculate the total entropy change for all your universe, and the word universe here meaning the system you are interested in plus everything surrounding it, it must be greater than zero. It will never be zero. It will never be less than, it cannot be less than zero. Let me give you an example. Here's a cup of coffee. That's your system. You are interested in the cup of coffee. It's hot. It's sitting on the table. Okay. How do I calculate delta S as the coffee is cooling down? S1 minus S2. You know, like you brought it, it was extremely hot. You put it there, you waited for 5 minutes, it's cooling down. There's an entropy change that happened. You will learn in thermodynamics that a simple way to calculate that with some assumptions is delta S is Q divided by T, right here. The Q, energy you lost, you know, when it's cooling down, you lose energy, right? Makes sense. Divided by the temperature of how hot it was. That's going to give you a delta S, and it's negative. You know why it's negative? Because the entropy is dropping. It's getting better because you're cooling it down. Actually, entropy is dropping for the coffee. But the coffee is sitting on the table in your room. When it did that, if I ask you calculate the delta S of the room, you say, well, heat was added to the room. This is Q. And the room was sitting at a T cold temperature. That's T cold. No, the room is colder than the coffee, the boiling coffee that you brought. And that's a delta S of the room. If I tell you, give me the total delta S of your coffee and your surrounding system, the room, your universe, that delta S is greater than zero. Take a look again. It's the same heat transfer that you took from the coffee, you put in your room. But if you divide by a large number, T hot, the coffee was hot, this will be a small number. And the Q divided by the T cold, smaller number. This is a bigger number. Sum both up. That's is going to be a positive number right here. Delta S is a positive number. So the generated entropy always have to be greater than or equal zero. In an ideal life kind of thing, it's zero, but typically it is not. So now you feel good about entropy. It allowed you to know how efficient your engines, your compressors, your turbines are, like we discussed here. And they taught you how energy has to flow in a certain way and obey that law. You see, you've heard about perpetual machines. And I'm amazed how many videos I see that are deceiving people. You know, there's no free lunch. Second law of thermodynamics say that things happen in a certain direction and they have to obey the order of that direction. Here is one video that say, you know, perpetual machines, like they tell you, we're going to put a rubber band here and a rubber band there, and then push the thing once and it keeps rotating forever. You've got power forever for free. This is a violation of the second law of thermodynamics. Inefficiencies and friction will make it stop. It will never continue forever unless you pay power. I have seen many people going for making an IP, intellectual property, and it's a shame. One of them was, he said, I'm going to bring a generator, a large mass, a dangling rod. You're going to push it, and then it will keep doing like this. And then we keep generating power. And I ask myself, did this person ever played with the pendulum? Did you hold the pendulum and let it go? And see it doing all this and fading away and stopping because of irreversibilities, because of the second law of thermodynamics, because it has to stop. And the only way to make your pendulum generate is if you keep pushing it with your hand, which essentially means nothing. You're just doing the work. All these things I said, there was another video of that guy. He said, I'm going to be driving my car, and he puts a fan on the car, a turbine, if you will. And if you are not comfortable with the term turbine, I think you are. You've seen those big wind turbines. He's putting it on his car, and he says, well, I drive the car. It's an electric car, and I put that wind turbine, and it charged my battery, and I'm driving for free. That violates the second law of thermodynamics. It's like you think there's a free lunch, and there is no free lunch. The energy that you are putting into the vehicle, you have to put more because you are actually the reason the turbine is spinning. Net balance is zero. In fact, you're going to lose more. Like if you do this exercise I just said, and you had to charge your car once every 5 days. So you add to it that device and you start driving it. You were charging every 5 days, is that right? You're going to charge every 4.5 days. It's going to get worse. Entropy says that. It says you have to pay extra for all the irreversibilities. You can't generate something from nothing. Enough for this concept, and let's move forward. Let's move to something a little bit easier, a little bit you can connect to really quickly and simple and easy. Mass flow rate, very important for us. That's not the property, but it's extremely important quantity. M dot. You see, M dot, as it implies, is mass flow rate. Just think about the definition for a second. Mass rate, the rate by which the mass is moving. So when I tell you that your, the jet engine has 300 kilogram per second flow rate, 300 kilogram every second, 300 kilogram of air, right? That you start relating mass flow rate. You see these devices here, you go from just a gasoline injector, this teeny tiny, and then you go to a gas furnace like the one that sits in your own home, to a car engine, to a diesel engine a little bit bigger, to the boiler. You see this thing sitting back there is a boiler sitting back there. Look at the size, tremendous. Boilers are very large. Jet engine, steam turbine, and rocket. Then, really at the end of the rocket. Take a look at the numbers here. See the rockets. 13,000 kilogram per second. You see, imagine you are an engineering student. You are solving a problem for this jet engine. You are calculating the airflow rate, and you finished your problem, and then you said m dot air is 1 kilogram per second. This is an engine that is flying an aircraft that is, 787, and you are telling your professor or the person who is checking on you, are you an engineer or not, 1 kilogram per, what is 1 kilogram per second? I can get some tomato, a bag of tomato that is 1 kilogram, and you are sitting here, and each second I throw 1 1 kilogram at you. That's the tomatoes. 1 kilogram. And you'll be able to pick it. It's going to be a little bit heavy, but just 1 kilogram per second. Every second I throw on you. How do you think that the jet engine that you see in the movies, the very large, all the things, but when you see the cars, when the couple videos that show when the car goes behind it with the jet coming out, it flips a car, it flips a truck, it flips, right? So it cannot be 1 kilogram per second because you don't have a feel for it, right? To the very small, like the gasoline injector in your car, this very small, teeny tiny injector is in grams per second. Very small amount, grams per second. And this makes sense. Imagine you are solving a problem for your gasoline car, right? And you're giving your professor the estimate. Then when I estimated the amount of fuel per injector, it is 5 gallons per second, right? Think about that now. Sit and think. 5 gallons. Every second your car is running. One injector takes 5 gallons. You have no engineering sense. There's no engineering sense there. That number has to be an extremely small number. The car runs for days with just 17 gallons for days, right? There's no engineering sense. So very important to have engineering sense. M dot is the mass per unit time. Units can be kilogram per second, kilogram per hour, power per second, power per hour, right? Depends on the units you are using. Build a feel for it. M dot is calculated by multiplying rho A times V. It's a very famous formula. When you want to calculate the mass flow rate, you take the density, multiply by the cross-sectional area, multiply by the velocity perpendicular to that area. This is very important formula, very simple, very important. Take care of the units. This is kilogram per second, kilogram per meter cubed, meter squared, and meter per second, right? This is very important. If I give you 3, you get the 4th. Any 3 of these, you get the 4th one, right? Very good. So now we know what is mass flow rate. We know mass flow rate is important. Let's move to measurement of mass flow rate. So it's important. We need to know how much fuel we are burning. We need to know how much the aircraft is burning fuel per unit time. We need to know the number. We can use it in engineering design, calculations. So how do we measure it? Well, there's direct measurement, and one of the most famous and most accurate device in measuring mass flow rate is Coriolis flow meter. It looks something like that, not necessarily. Don't let this schematic fool you. So when you walk in a test cell, for example, or an industrial facility, if you don't see that U-shaped, you say, oh, that's not. No, sometimes it is actually U-shaped, but it's covered. It's contained in a cover, so you cannot see that U-shaped. But it is when you remove the cover, you will, see something under it that looks like that. So that's Coriolis flow meter. I'm not going to go over here how it operates or any of that. Again, as I'm doing today, I'm just telling you the name of the device so you know, and that it's very accurate. So one day you are working somewhere as an engineer, they tell you, hey, we want to measure the mass flow of this fuel we are pumping. And you tell them, let's get a Coriolis flow meter. Then they tell you, oh, that's Coriolis is very expensive. It's very expensive, the most expensive thing we can bring for that. You say, well, because it's the most accurate. It's going to be very accurate. Give us the accuracy that we need. So that's what I'm trying to communicate to you. That's a direct measurement. Now, indirect measurement for mass flow rate, very common, very famous are the Arvises, the Venturi, sonic meters. They all indirectly, through pressure measurement and temperature measurement, density, and things of this nature. I'm not trying to cover that here, but just want you to know you can use these. They are much cheaper devices but not as accurate as the Coriolis, except the Venturi. There is the turbine flow meter, and this essentially looks like a turbine that spins, and the spin rate relates to the velocity, knowing the area, again, indirect measurement of the flow. And the ultrasonic flow meter, where you have a transducer and a transmitter and a transducer, and then essentially you correlate this ultrasound as it goes through the fluid, and you translate that into a mass flow rate. Just want you to know some name of these devices. Volume flow rate. Well, you guessed it right. Volume flow rate, if I tell you the volume is flowing at, 1,000 liter per minute, 3 gallons per minute. These numbers mean something for you. You see, we like volume flow rate. It expresses the volume moving per unit time. If I tell you your faucet at home is around 1.5 to 3 gallons a minute, what comes to your mind? Say, if I turn the faucet on, open all the way, get a gallon, and stop my stopwatch, I fill, empty, fill, I'll fill 1 to 3 gallons every minute, right? Engineers, they like things that make sense and that they can put to work. You see, when I tell you, for example, that your amount of water that you consume daily, every person needs 50 gallons. It's important for you because if you say, if I get 50 gallons a day, 50 gallons I need a day, then in a month I need a 1,500 gallon. Now you're going to go buy a tank she without even knowing. You now suddenly felt that you know the size of the tank you will buy to get you the water you need for a month, for example, right? So volume flow rate, we like it because it relates to the volume where the thing is contained and I am using it, if that makes sense. Now, for example, this is why engineers came up with the miles per gallon. Think about that. Your car, you say miles per gallon. How many miles per gallon? And everybody here is relating to it really quick. So you say, I get 20 miles a gallon. 1 gallon gets me 20 miles. So 10 gallons. And you can estimate that, okay, I need to refuel once a week. Or I'm driving a car that is, burns 7 gallons per mile. So I need to fuel every 3 days or 4 days, something like that, right? Volume flow rate. We tend to use CFM, right? CFM is cubic feet per minute for air. We like that number for air. You see, for water, we use gallons a minute. For the fire hydrant, gallons a minute. You know that fire hydrant where they use if God forbid, there's a fire? That can put about, 500, 600, 700, 1,000 gallons a minute. Just think about that. Tremendous amount of water from a hydrant. Now, it happens that when we deal with air, we like CFM. Why do we like CFM? Why do we like cubic feet per minute? Why do we like cubic feet every minute? Think about it. Engineers use numbers that make sense. You see, you're going to buy an HVAC system for your house. And let's say that your house is 26,000 feet cubed. You know the volume. Your house has a volume. And there's the air sitting in this volume and it's very hot. Temperature is 80 degrees. You turn the AC on. That AC is going to take that air, cool it down and pump it back. If your HVAC is 1,000 feet cubed per minute, 1,000 CFM, your HVAC pumps 1,000 cubic feet every minute. How long does it take your AC to pull all the air in your home and pump it back cold? That's a very important, number to build a feel for. And in this case, that would be about, 16 minutes. So if that's your system, if that's your home, you turn the AC on, you're probably going to wait, let's say temperature 80 degrees. You're going to wait minutes, 10, 15, 16, until that. So we like it because it expresses and relates to what we are trying to achieve. The amount of air we are moving per minute, in this case, relates to that. Right, good. You see a dam, a water dam here. You know, these water dams, tremendous. You can see videos on YouTube. That's a 10,000 meter cubed per second. Now, think about that number for a second. It's humongous. You know what is 10,000 meter cube? You know what is 1 meter cubed per second? You know, 1 meter, that's about 1 meter. Like from the tip of your finger to here, it's about like, you know, here, like 1 meter. So 1 by 1 by 1, this is called 1 meter cubed. If I fill 10,000 of that in 1 second, what is the amount of water that we have? It's just, do you think a human being can survive this water falling on the person? Right? So you build a field, you have a feel for what does the number mean, the magnitude, and so on. This volume flow rate is area times velocity. Area times velocity. You know, mass flow rate is rho AV. Volume flow rate is just AV. So the relationship between m dot and volume flow rate, m dot, rho times Q. That's the relationship right here. M dot is rho times Q. This is how you transfer it from being the mass you are pumping to the volume you are pumping. Right? Okay. How do we measure it? Well, positive displacement meters, like gear pumps and so on, they meter the amount, the volume that is being pumped. Rotometers, like this device is a rotometer, right? Turbine flow meters, ultrasound, differential, all these can actually get you a volume flow rate estimate, if you will. And now you know this is very common, though simple, very common, this rotometer for HVAC and so on, if you will. We are going to move to thermal conductivity. This is a very large lesson. Feel free to split it depending on your time and schedule, but I'm going to cover it in one video, if you will. You see, thermal conductivity is one of those very interesting properties, and it's extremely important for us. Thermal conductivity is how well a material conducts heat. See, if I have material and there is a source of heat hitting here, the heat has to move through the material to the other side. It has to move through it. If the thermal conductivity is high, it moves very easy. If the thermal conductivity is low, it moves very slow. Let me calibrate you and give you the feel. Your car, you are down in Texas on a very hot day, or you are down in Saudi Arabia, and it's 125 F, and I'm not kidding you, 125, 130 F. Your car is parked. Your hood is metal. You go down, you touch the hood, and it's blazing hot. It burns your hands off. Because these metals have a reasonable thermal conductivity. They pump that very well. But deep inside your home, and the same sun is shining on your walls, it feels hot, but you can touch it. It's way better. Why is that? Because there are lots of insulation that makes it difficult for the heat to transfer. You see, when you buy these hot mugs that keep things hot and cold, how do they work? Like, what are they exactly doing? See, what they do is they have around where you put your stuff an air gap. So there's an air gap around it. Why air? Because air, see this air here? Thermal conductivity is very poor, very small number, 0.25 watt per meter Kelvin, meaning that air, if it's stagnant, if it's standing still, stagnant air, and heat tries to pass through it, it's very difficult for heat to pass through it, right? So this thermal conductivity, if K is high, you move heat quick. If K is low, you move K slow. So which is good and which is bad? There's no good and bad. It depends on what you need. If you are trying to insulate I'm trying to insulate. I don't want heat to move. Then you look for insulators. Like here, you see insulation is close to the air. So air is an insulator, right? Watt per meter Kelvin is the unit of thermoconductivity. How about if you want to move the heat? I want the heat to move. Where do we want the heat to move? Let's get an example. Well, your radiator. You know, in your car there's a radiator. This radiator, what it does is it's trying to cool down the hot water. So for what you want to do is actually move the heat. I want to remove that hotness. Then your radiator will be made out of copper or aluminum, because look at the K here, man, look at that. 400 watt per meter Kelvin, 200 watts, very large numbers. So you're going to move the heat very easy. And that's the application that you need, right? So when I go for a heat exchanger, is where you will see copper, aluminum, and sometimes not much you can do, because you cannot use aluminum or copper at some extreme conditions, and you have to go with steel, and steel will be way less than these, which means that it's not going to be as good, it's not going to be as efficient, it has to be larger in size, but that's okay, because that's the application. There's nothing cannot do better than that, right? So thermal conductivity concept is extremely important. You build a feel for the numbers, what the numbers mean, what it is used for, and this equation is extremely important equation. You will see it in many of the applications as you progress in your career, but essentially what it says is something very interesting, that the heat transfer is proportional to the temperature gradient, and that proportionality constant is K. If you're not comfortable with the things I just said, that's perfectly fine, but all what it is if you bring a thick wall, you put a temperature here, large temperature, 400 degree, and you go to the other side, the amount of heat, the temperature that you will get, depends on the thermal conductivity of that piece of thing, that K. The amount of heat is proportional to that, right? That's all. This is what it means. Viscosity. You know, viscosity is one of the concepts that are simple to build a feel for. It's mu, pronounced as mu. Units are Pascal second or centipoise, if you will. It indicates how sticky the fluid is, right? So immediately what comes to mind when I say that, honey would be very viscous. Water will be not at all. Air would be, man, I mean, just air. Do you imagine air? You see, if I bring this and fill it with honey, and I put a spoon in and I'm trying to spin, and I'm putting all this effort, why is that? Because the honey is resisting, the honey has high viscous forces, high viscosity, it's so sticky. So I can't, right? How about if it's water? No, water is easy. Boom, boom. No problem. How about if it's air? Nothing in the cup and I'm spinning the spoon, right? So the numbers are, we like to use centipoise. Now, believe it or not, I forget the name of the scientist who developed that concept and, this, viscosity and measurement, but you look at the reference. Water was 1 centipoise. Actually, this is how the centipoise kind of came to existence, because it's measuring relative to water. See how engineers are very smart and how scientists are very smart when they want to put a feel in a number. You see, if I tell you the water is 1 centipoise, so you know the water, how it resists motion. So when I tell you this is 5,000 centipoise, you say, oh man, this is 5,000 times the water, that feel that I know for the water, right? Immediately resonates. Or I give you an oil, the engine oil, like the engine oil that sits in your car. I say that's 100 centipoise. I say it's 100 times more than water. You cannot go to your car and put water in it instead of oil. It won't even spin it won't even continue a minute. You're not even going to get a minute out of that, because the water is runny. It's not going to lubricate the surfaces. We want it to lubricate. It has to have viscosity to it, right? How do we measure that viscosity, dynamic viscosity, all the things we've been discussing here? Well, we measure it in rotational viscometers, capillary viscometers. Right, these devices, you put it in, it's very straightforward. You press a button, it gives you a reading. Here you go, you've got the viscosity. You see, there's another type of viscosity called kinematic viscosity. The other one was mu, this is nu. And the units for that is meter squared per second, or centistoke. CST, centistoke. Why do we have this nu? Why are we talking kinematic viscosity? Well, you know, nu is mu over rho. Nu is mu divided by rho. I should have added that formula here, so I don't have that. Let's see if I'm going to try to fix it after the video and maybe just add it and keep the... I'll see what I can do, but worst case scenario, it's mu from the other slide divided by rho. Well, what we found is, you know, again, engineers are very smart, that it's not only how sticky, it has to do with its own weight as well. When engineers went to design pipes that, you know, they want to transfer water from a river to your home, they want to transfer oil from where they drilled it to where it's going to be processed, they want to transfer these fluids and pipes and move them around, like your car, the gas from the tank to the engine, they move things. They found out that the pressure drop, think of it as the energy needed to move the thing. You know, you need to move it, you're going to pay energy so you can move it. When you estimate that, many times you need the ratio of mu over rho. It appears there. And one famous place it appears, and it's called Reynolds number. There will be a separate presentation about non-dimensional numbers and thermal fluid sciences. For now, I want to share this with you. There's something called Reynolds number. The nu is there. See, this is the nu we are talking about. You tell me, okay, so why is this? Now, you will come to know that this Reynolds number is very important in knowing your flow structure. This Reynolds number, it's a number we calculate, that if it's less than 2000, it looks like this. Very smooth layers, called laminar flow. As if it's moving in lamins, very smooth. And if it's more than 2000, this is 200,000, you have a turbulent flow, jumping all over the place and mixing and moving around. There is no, if you put a dye, you put something in it, right? That's a turbulent flow. So you will tell me, but why are you telling me this? Why are you telling me laminar? Why are you telling me turbulent? Because I want to tell you that this nu comes into play in saying this is laminar or turbulent. And maybe you're going to double down on this and say, so why do I need to know it's laminar or turbulent? Because if you don't know, you will not be able to pump it. Because to pump it, you need to know the Reynolds to estimate the frictional drop on the pressure you want to put in. And I'm not trying to teach you that today, because again, at some point in time in future I will. But what I want you to know now is, in the engineering problem, where engineers are trying to design systems to move fluids, they have that popping up, mu over rho, and it's a property called nu. That's all. Just trying to tell you that it is important. You see, here is water, oil, and honey, and you are letting them fall under their own weight. You see, we said weight comes into play with the how viscous is it, the mu. Water will reach out very quick, oil is going to be coming second, and honey will be the lowest, if you will. Number wise, water is 1 centistoke, air is a fraction, and motor oil is 100 times that centistoke. All right, so that's it. We have spent about 2 hours together. Thank you for your time and thank you for your support. And don't forget to like and subscribe to the channel, as we're going to be putting more and more videos to help you be better at what you do. It's very rewarding to see people succeed. To me, one of the things that it's a God given, you don't give those things to yourself, but when I look in a person's eye and I see that this person came confused and it was difficult and heavy to understand something, and then you see that brightness in their eyes when they now understand and they feel better, it's a beautiful taste in my heart and mind. And I hope that this is how you feel now, and with time it's just going to get even better and better. Thank you so much, and see you soon in the next video. This is Bassam Abdel Nabi from ProReady Engineer. Take care and see you later.